Imagine a mountain so tall that climbing it means leaving the atmosphere behind. A peak nearly 3 times the height of Mount Everest, rising 21 kilometers until it terminates in a star-filled void. This is Olympus Mons. It sits near the Martian equator, spanning 600 kilometers from edge to edge. That footprint is wide enough to completely cover the country of France. Despite its height, the volcano is surprisingly flat. The average slope is a mere 5% gradient. If you stood on its flank, the incline would be so subtle that you likely wouldn't recognize you were standing on a mountain at all. Because Mars has a much smaller radius than Earth, the horizon is significantly closer, a mere 3 kilometers away at ground level. At the base of the volcano, the planet's own curvature hides the 21-kilometer summit from view. At this scale, the massive structure creates the illusion of a flat, high-altitude plain. It raises a difficult question. How do scientists actually calculate a 21-kilometer height on a dead planet with no oceans? On Earth, our definitions of height are tied to mean sea level. We measure Everest's 8,848 meters against the gravity-defined surface of our world's oceans. Mars requires a different benchmark, called the areoid. This is an invisible, mathematical sphere defined by the planet's atmospheric pressure. Scientists set the zero elevation at 610.5 pascals, the triple point where water can theoretically exist as a solid, liquid, and gas. Orbiting laser altimeters use this pressure baseline as a ghost sea level. From this invisible threshold, Olympus Mons towers exactly 21.2 kilometers into the sky. Using a pressure datum allows us to quantify its scale, but the mountain's existence is due to how it bypassed the geological rules of Earth to build itself. On Earth, moving tectonic plates prevent a single volcano from growing indefinitely. As the crust drifts over a stationary magma plume, it creates a chain of smaller shield volcanoes, like the Hawaiian Islands. Mars lacks these restless plates. It is a stagnant lid planet, meaning its crust is a single, immobile shell that has remained stationary for billions of years. Because the crust never moved, a massive mantle plume could act like a blowtorch in a single geographic location. Magma erupted from the same vent system repeatedly, piling lava flow on top of lava flow. This was aided by Martian gravity, which is only 1/3 as strong as Earth's. This lower pull allowed the volcanic material to stack to extreme heights, without the structure collapsing under its own weight. Olympus Mons is the physical evidence of a planet that went still. Geological stagnation, combined with weak gravity, allowed a single vent to reach the absolute vertical limit allowed by the Martian environment. The Tharsis region is a volcanic plateau dominating 25% of Mars. Olympus Mons is one of 4 giant volcanoes here. Its sextillion-ton mass is so heavy, this text notes a measurable mismatch between observed gravity and predicted crustal thickness. Roughly 3 billion years ago, the planet's surface could no longer support this lopsided weight. The entire outer shell of Mars, the crust and the mantle, slipped 20 degrees toward the equator. The growth of Olympus Mons forced a global reorganization. Its unchecked mass rerouted ancient rivers and shifted the planet's climate and gravitational axis. After an ascent spanning nearly 200 miles, you would arrive at the 80-kilometer-wide summit caldera. This is a landscape of high-altitude stillness, sitting far above the Martian clouds. This environment is possible because of the atmospheric scale height. On Mars, the lower gravity allows the atmosphere to expand further into space than it does on Earth. This chart compares pressure to altitude. While Earth's Everest sits within the bulk of the air, the summit of Olympus Mons hits a pressure of just 72 pascals. This is effectively a hard vacuum, sitting clear above the planet's global dust storms. At this altitude, the concept of a mountain peak merges with orbital space. To stand at the summit is to stand on the very edge of the Martian void. In the 19th century, astronomers using equipment like this noticed a white spot poking through the red dust of global storms. They called it the snows of Olympus, guessing even then that it must be exceptionally high. We didn't confirm the scale of the structure until 1971, when the Mariner 9 probe arrived in orbit. It revealed not just a mountain, but the largest volcanic edifice currently known in the solar system. Earth's mountains are temporary features, continuously built and destroyed by the collision of plates. Olympus Mons is the opposite, a frozen monument to a world that stopped moving billions of years ago, waiting in the silence for our first steps.